Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2011, problem number 4. Let A be a unital ring, let n of A be the set of nilpotent elements of A, let A cross be the set of invertible elements of A, and let Z of A be the center of A. We wish to prove two things. First, if Z of A equals A, then we have the following set equality. A, so units of A plus nilpotence of A equals units of A. And B, part B, we wish to show that if A is finite, and if A is some element of our ring, and if A plus units of A is a subset of units of A, then our element A is nilpotent. It's a very nice problem from ring theory. I love it. And here are my hints. Or first, some definitions. First, units A star. Units are these elements which have their inverses. It's all the A's for which there are B's, such that AB equals 1 equals BA. Nilpotent elements are those elements such that A to some power equals 0 for some positive integer k, and center of A consists of every element which commutes with every other element of our ring. So A is in the center of our ring if for every B, AB equals BA. And now actual hints. For part A, since center of our ring is A, that means that our ring is commutative. Just that. And maybe you may wonder, what does this notation mean? Set A plus set B. Well, set A plus set B is defined to be set of all elements A plus B, where A is in A and B is in B. It's used multiple times in this problem. So to show that units of A is a subset of this set, this is trivial. To show the other inclusion, it's tricky. Suppose that U is a unit, N is nilpotent, so n to the power of k equals 0. Suppose that this happens for some odd number k. You can assume this without loss of generality. And then consider u to the power of k plus n to the power of k. So unit to the power of k plus nilpotent element to the power of k. And see what's happening then. And for part B, show that first some results, further results, show that if U is a unit of our ring, then 1 plus AU is again a unit of our ring, and then show by induction that 1 plus A squared and so on, plus A to the power L minus 1 is invertible for all positive integers L. And the last two hints, since our ring is finite, this set, which consists of A squared, A cubed, cannot be infinite. So two elements in this set must be the same. A to the power of k equals A to the power of k plus L. Use this to get this equality and try to finish this problem. So give this problem a try, and I will see you in just a minute. Right. So let's start with part A. As I said, since Z of A, center of A equals A, our ring A is commutative. So AB equals BA for every two elements. Alright, now notice that A star is obviously a subset of A star plus nilpotent elements of A. Why is that? Because 0 is a nilpotent element of A. Yes? So for example, U can be written as U plus 0, obviously. So this is true. What about the other inclusion? To prove the other inclusion, let u be some element, invertible, and let n be some nilpotent element. Well, since n is nilpotent, we can assume that n to the power of k equals 0 for some odd positive integer k. Well, why is that? Well, because if n to the power of k is 0, then n to any higher power is 0 as well. So we can choose odd exponent. Alright, and now let's notice the following. U to the power of k plus n to the power of k. Since our ring is commutative, we can make this well-known factorization. It's the same as u plus n, u to the power k minus 1 minus u to the power k minus 2 times n plus u to the power k minus 3 times n, and so on, alternating between pluses and minuses. In the end, u n k minus 2 plus n k minus 1. This only works because we assume that our ring is commutative. And now let's see the following. What's happening? Well, notice that n to the power of k, we assume that it is 0. And since u is invertible, u to the power of k is also invertible. So we can write actually the following. Number 1 equals u plus n times this times u to the power minus k. We know that it exists. And that means that this element right here is invertible. What's its inverse? Well, its inverse is this entire expression. So u plus n is invertible, i.e. the set of invertible elements plus the set of nilpotent elements is a subset of invertible elements. And now combining this inclusion with this inclusion, we get equality. This closes part A. Now for the part B. Now we drop the assumption that our ring is commutative. Now we wish to prove something else. We wish to prove that we assume that A plus units are a subset of units, and we wish to show that A must be nilpotent. How can we do it? Well, I will proceed by proving 3 claims. Claim number 1. I claim that if U is invertible, then 1 plus AU is also invertible. How to prove it? Proof of my first claim. How can we prove it? Well, notice the following. We assume, maybe let's write it to remember it. We assume that A plus A inverse is subset, A units is a subset of units of A. Let's remember that. All right, proof. Notice the following. Proof is very straightforward. 1 plus AU, we can actually factor out U. So it's U A plus U inverse. Maybe also let's do it on the right hand side. Yes. Now it's right. Alright, but now this is invertible. How do I know it? By assumption, because U inverse is invertible. It's obvious if it's invertible, because it's inverse of U, but this is invertible. By assumption. By assumption. Alright, and this is also invertible. And product of two invertible elements is again invertible. So this is again is in A star, which closes the proof of my first claim. Claim number 2 is much more interesting. I claim that if L is a positive integer, then 1 plus a squared and so on, plus a to the power L minus 1, this entire thing is also invertible. Proof. I will prove it by induction. Notice that it works. It works for L equal 1, because then we have 1, and for L equals 2, because then we have 1 plus a, and 1 plus a is some invertible element plus a. We assume that it's again invertible. And now let's assume, and now notice the following. What will happen if I will take, or maybe, you know what, I will write it the following way. 1 plus a squared plus a to the power of L minus 1 plus a to the power of L. I can write it in the following way. It's 1 plus a squared, but this time just to a to the power L minus 1. Is it right? It is. Alright, and now this is invertible by assumption. Maybe I will write comment. Let's assume that 1 plus a squared and so on plus a to the power L minus 1 is invertible. We are doing inductive proof. So this is invertible by assumption. Which means that this entire thing is also invertible by claim number 1. Which means that our entire sum is invertible, which closes the inductive proof. It closes the inductive proof of my second claim. And third claim, which follows immediately from the second claim, claim number 3, is that for every positive integer L, a to the power of L minus 1 is invertible. Proof is very straightforward. Proof. Well, a to the power L minus 1, it can be factorized as a minus 1, a to the power L minus 1, plus a to the power L minus 2, and so on, plus a plus 1. And notice that this is invertible by assumption. Yes, why is that? Because it's a plus some unit. A plus unit is by assumption invertible. Maybe let's write it because a plus units are subset of units. And the second part is right here, is invertible by claim number 2. Again, product of two invertible elements is again invertible, which closes the proof of my third and final claim. And now, what now? What now? Well, now I will use the fact that my ring is finite. Actual proof of B. Since f is finite, since A is finite, the following set, the set which has a squared, a to the third power, and so on, this set must also be finite. It also must be finite, which means that two elements of this set must be the same, at least two elements. Which means that a to the power of k equals a to the power of k plus l for some positive integers k and l. Yes, it's in principle it's pigeon hole principle. Right. And now let's take this equality and let's write it in a different way. We can write it as a to the power of k plus l minus a to the power of k equals 0, right? And now we can write a to the power of k, a to the power of l minus a to the power of k equals 0. Now we can factor out this and we get 0. And now we'll finally use our claim number 3. This is invertible. By claim number 3. Which means that I can take this equality and I can multiply by a to the power of l minus 1 inverse. And I have finally the following. A to the power of k equals 0, which means that my element A is nilpotent, i.e. A is nilpotent. And that closes our proof. We have demonstrated that A is in the set of nilpotent elements of our ring. Beautiful problem. I just love solving algebraic problems. To be honest, algebra is such an elegant branch of mathematics. From a relatively small set of axioms, many things can be proved, and this is one of them. So yes, thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.